Everyone. We're going to push ahead and start the next session while people are coming in. And the subject or the focus of this session is on early time observations. Okay, so quiet down if you. We're going to start here. Stay on schedule. Follow Ori's directions. So the session today is, or right now, is early time observations, as also focus on ultraviolet. So put on your shades. And first up here is Azalee Bostrom. She's going to provide talk about overview early ultraviolet observations of supernovas. All right.
Awesome. Okay, so I have been asked specifically to tell you about early UV observations of supernova using SWIFT and HST. I will have one slide on IUE, the International Ultraviolet Explorer, and one slide on GALEX, which I think have also provided us with really interesting ultraviolet results. And I want to say up front that it is an impossible task to summarize all UV results of supernova, and so I apologize if I missed your favorite results. I had originally a 30-minute talk, and I had to cut it down, and even that is missing things. So I want to start off by saying that this field, I think, is really in its infancy. We are at a point where we have 5, maybe 10s of a given type of supernova in the ultraviolet, and that's over all different epochs. That's not all at the same epoch. And the reason for this is that it's, first of all, very challenging to get ultraviolet observations because you have to go to space. This is not something you can do from the ground. And the ultraviolet in general fades rapidly over time. So this is an example of a type 2 supernova. You can see that, well, the optical is very flat. The ultraviolet fades over the first 15 days by magnitudes. At the same time, because you have to go to space, instruments like HST, which are our most sensitive ultraviolet instruments, take a lot of work to trigger. So this is a series of all of the things that had to go right in order to trigger the UV spectra of supernova 2022 ACO. This is the earliest far UV spectrum we have of a type 2 supernova. You can see we detected it within 24 hours. We very rapidly confirmed it. We announced the discovery. We got multiband imaging showing that it was UV bright. And we submitted our APT so that planning could start happening all within the first 36 hours since explosion. We got our first SWIFT images within 2 days, and we submitted our disruptive TOO shortly thereafter. They were all of this happened, and the observations were scheduled within 3 days. They executed 2 days later, so that all sounds like this very rapid sequence of events, but that still meant that our first observation was 5 days after explosion. And so I think one thing that I want to look to the community to have discussions about is how can we speed this up? And I think things like a cross help, but I also think understanding what are the limitations and how as a community can we help people at Space Telescope to get this process happening more quickly. And so to show you kind of where we are, this is a recent plot showing the number of detections in the optical in red and in the ultraviolet in blue. And you can see that while we're close to kind of getting all of the discoveries within a day of explosion in the optical, we're not getting a similar completeness rate in the ultraviolet till about 2 days after, or 2.5 days after explosion. So this is an area that we are pushing on, and I think is recognized by future missions. Both ULTRASAT and UVEX have very rapid turnaround times, which I hope will help to resolve some of this. So even though the ultraviolet is hard, there's a tremendous amount of information that's contained in the ultraviolet, and it's still worthwhile to study. This is where the black body of most supernova are peaking in the first week post-explosion. If it were a black body, in many cases we'll see it's not, and there's a lot of flux that's absorbed, but that still gives us a lot of information on the supernova and where the energy is going. The UV forms in the outer ejecta, which means that it's sensitive to conditions of the stellar surface, like composition, like the radius of the star that exploded, as well as that outer ejecta, like density and temperature as the supernova evolves. And because this field is so I'm not going to say young because we've been observing supernova in the UV for 30, 40 years, but we don't have that many spectra. And so it means that the questions we're asking are how diverse are the UV observations of a given type? Do they all look the same? Do they look different? Are there clumps in them? And then what is the meaning, kind of the physical cause of this uniformity or the diversity that we see? So with that, I want to introduce you to some of the stars of the observing, which is the observatories themselves. This is my one slide on IUE. So IUE operated from 1978 to 1996. It had far UV and near UV wavelengths. Here's an example of supernova 1979C. You can see the amazing detail captured in the spectrum. So don't forget about IUE. MAST archives these, but it archives them in a file format that I could not figure out how to read. So I'm giving you a link that I found that archives FITS formats so that you can, it's very easily searchable and you can find UV spectra there. So moving on to the Hubble Space Telescope, this began operations in 1990, still operating. It has always had UV instruments on it. It currently has COS and STScI. COS goes all the way down to 815 angstroms, so it has EUV capabilities. The challenge with HST is the TOOs. So there is one TOO awarded every cycle that has a less than 48-hour turnaround, and that you cannot observe the far UV with. And then there are around 9 awarded with a 2 to 5 day turnaround. And that's it. So as a community, this is a place that I think we can collaborate to try and collect the best spectra rather than competing with each other I think to the detriment of our field and maybe not getting those observations. I think we've really benefited from the UV initiative, which has prioritized ultraviolet observations, and the fact that the archive produces 1D extracted spectra that generally are very good and have recently come up with these Hubble Advanced Spectral products, which combine multiple optical elements and different observing epochs for a given target. And then finally, the Swift Space Telescope began operations in 2004. It's not quite as far UV. The wavelengths start at 1700, but that's still much better than you can do from the ground. This has really benefited from having non-general investigator TOO programs where anyone in the community can trigger interesting events. And then also the fact that these data are public. And then I also want to highlight 2 things. One is the new Urgency 0 TOO, which gives a minute's response time. I think this is going to change even those rapid responses to even more quickly. And then the SUSE archive, which has already been called out, Peter Brown and his team have put together not just images, but light curves of all of these different supernovae that you can go directly to. So with that, I want to give you a little introduction to what different types of supernova look like in the ultraviolet, starting with type 1a supernova. In many ways, these are the best studied. We have samples of tens of supernova in the UV. And this I found actually was I discovered this while I was flying here and looking at these light curves. So supernova 2011 FE and supernova 2017 CBV are very well studied type 1a supernova. And you can see in the UVM2 filter, which is a mid-UV filter, they are different by a couple orders of magnitude at early times. And so if we look at the high redshift universe and we want to try and use these supernova to determine distance, we need to figure out how we can standardize the diversity in the light curves that we see. And so it's possible that we can do this with spectra and looking to the spectra to try and understand this. So this is using Swift spectra. Most of the spectra I'm going to show are from HST, but Swift for bright supernova can still get really nice spectra. And you can see that there are some trends in the light curve that are related to the light curve. So fast evolving supernova seem to be near UV bright and maybe suppressed in the mid UV, where the slower evolving light curves seem to have the opposite effect. You can also see that there's a metallicity effect where there's a lot more mid-UV suppression here in higher metallicity cases. And so it's possible that these types of trends can be used to standardize the UV, but right now we have maybe 30 supernova that we can do this with. It would be great if we had more and we knew what was going on at wavelengths below this. So moving on to superluminous supernovae, these are the one supernova that are actually UV bright. So more than 50% of their flux comes at wavelengths shorter than 2,500 angstroms. We think this is probably because they are forming in low metallicity environments, and therefore the outer ejecta are low metallicity. In addition, this probably also tells us that there's not a lot of mixing of the elements that are created either during the progenitor evolution or the supernova explosion itself, that metal isn't mixed all the way out into the outer ejecta. Here you can see there's a very large diversity in the flux and the different features that are present, so that it's very challenging you can't come up with a single template to understand superluminous supernova. And this is one of the fields where this is it. So it would be great if we could collect more observations and try and understand how are these evolving? What do they look like if you catch, different superluminous supernova at the same phase? Do you see this diversity in temperature and things like that? So moving on to core collapse supernovae, the challenge with these is that they fade rapidly with time. I've already showed you supernova 2022 ACO. Here are more swift observations. Here's the optical from the ground. Or no, sorry, this is optical from Swift, but you can see that the V and the B band are pretty flat, whereas the UV really plummets and maybe eventually plateaus after about 20 or 30 days. Even for the stripped envelope supernovae, you get your shock cooling phase, which is often not caught by Swift, and then you can get another rise and decline. But you can see that things still fall off pretty quickly. And so I think this makes it challenging to observe these, and you need these early time observations. For stripped envelope spectra, the UV is very much suppressed. And this is because you have metal lines that are broad, and so they all blend together. And what's interesting is that this is often attributed to metallicity. However, these objects here have a factor of 10 range in metallicity, but still all show kind of the same UV suppression. And so this could be telling us that we are getting the mixing of iron group elements out into the outer ejecta, and that effect is washing out or superseding the metallicity effect. So finally, moving on to my favorite supernova, which are the type 2 supernovae. So Saurabh showed this. This is supernova 2022 ACO. So this is that far UV spectrum that we got with that timeline that I showed you. We have spectra here taken one day apart, these first three. And you can see how rapidly this evolution happens, how these metal lines are suppressing the UV flux more and more until by day 20, there's almost no UV flux. However, at the same time, when we look at different supernova in the ultraviolet, we see what I think is a range and diversity in the spectra. So here I've normalized everything to around this wavelength range. You can see the optical looks pretty similar. We see some variations in H alpha, but the UV looks very different. And in particular, supernova 1999 EM is still a puzzle to me. This is one of our most prototypical type 2 supernova, and it has the weirdest UV spectrum. And so one thing that I would like to explore, for supernova is great, but it's really hard to figure out, what are the trends? Are there common groupings here, or do these all look very different? And what is the reason for this diversity? Is this telling us about explosion properties? Is it telling us about CSM properties? And so a big theme of this is just we need more observations. Okay, so now that you've seen what supernova look like in the ultraviolet, I want to talk about different uses for these observations. So the first is figuring out what the progenitors of type 1a supernova are. So there's the double degenerate scenario and there's the single degenerate scenario. In the single degenerate scenario, your supernova explosion hits your non-degenerate companion. That creates a shock that should be UV bright. So here are the best models that we could fit. This is for 2023 BEE. And you can see that they're over-predicting the flux, especially in the mid-UV and far UV. But we still do see this bump here in the UV, which could be indicating that maybe there's something wrong with our modeling, but this is maybe still a non-degenerate companion. But this is something that getting even earlier observations and knowing what is going on here would be really helpful to help fill this out. Often we have one, maybe two UV points that show this bump. This is my slide for Galax. This is looking at shock breakout. So Galax in the near UV caught when the photons are first reach a low enough density that they can break out of the star. This creates a UV flash, which should fade rapidly over time. Here you can see that rapid fading, although I will say that this was not as rapid as initially thought, which may be telling us that the progenitor had a larger radius or there was some kind of extended CSM. And this is something that ULTRASAT is specifically going to be looking at and should provide us with much better statistics and understanding of what's going on. Shock cooling, so after that shock has broken out, your ejecta expands and cools. And so how it expands and cools over time can tell us about the radius of the progenitor, the velocity of the shock, and possibly the mass of the hydrogen envelope. So here is a model from a paper that Manisha did on 2022 AXU. And you can see that while these models fit the optical pretty well, they're missing the ultraviolet. And in a sample paper, Irani et al. Found that there were two different types of model fits, one where they could fit the early rise and one where they missed the early rise. They showed that regardless of whether they fit or missed that rise, they were able to constrain the radius, but that these radii maybe tended to divide into a smaller radius and a larger radius. So even when the models don't fit the data, they're still potentially telling us about the progenitor, and maybe this is giving us information on red supergiants and how they evolve. So looking at mass loss in massive stars, mass loss has small effects in the optical, and they tend to fade fairly quickly with time. But in the ultraviolet, they are strong and persistent. So here, these models have no mass loss or no material surrounding them, and this has the highest level of mass loss. And you can see this spread of magnitudes that allows us to both identify these low levels of mass loss and differentiate between these different scenarios. And so we were able to do this for Supernova 2023 IXF. Eris, I'm sure will tell you more about this at later times. But you can see we have these narrow features here that were observed in both the ultraviolet and the optical, but which disappeared after a week. And so those indicate very dense CSM. Here on the density plot, these correspond to mass loss rates of 10 to the minus 2 to 10 to the minus 3 solar masses per year. But we continued to monitor this in the ultraviolet, and we found that even after those narrow lines disappeared, there was elevated ultraviolet flux, but how much ultraviolet flux there was faded with time, which we could then match to models and show that the mass loss rate and the CSM density was changing and fading with time down to by day 66 or somewhere, a couple hundred years before explosion, that this progenitor star maybe had fairly normal red supergiant winds. And so we can actually use UV observations to map this mass loss history after the optical signatures have faded down to very low mass loss rates. And then the conditions of the outer ejecta. So I mentioned that our UV photons are originating from the outer ejecta. One thing that was really interesting in monitoring Supernova 2023 IXF that I've noticed other places in the literature is that when you have the full UV and optical SED, it's challenging to get the fluxes right for both regions. And when we don't have one of those, we can just scale the other one down. But when you have that full wavelength range, you usually overestimate the optical and underestimate the ultraviolet. And so we looked at how could we possibly modify these models, and it turned out that they were insensitive to a lot of different things we tried. We tried increasing the mass loss. We tried changing the treatment of the radiation. None of this worked, but when we introduced more clumping into our model, it fixed the problem. So this is a case of one, but I think it's very interesting idea to be able to put all of this together and use it to constrain what's going on in the outer ejecta and possibly those properties. And then finally, the UV is essential for understanding the high redshift universe. So here I'm showing you far UV and near UV wavelengths that then are getting shifted into the optical. These are the Rubin wavelengths. And then for Roman and JWST, you can imagine taking these out to even higher and higher redshifts. Here is an example where from the JADE survey where we're already seeing UV SEDs or SEDs that are moving into the UV. And so in order to understand these observations, it's really helpful to have to know what this should look like in the local universe. And at the same time, I think that these observations are going to tell us something about what these supernovae look like in the high redshift universe, and maybe give us even larger statistics in the ultraviolet. And this is for the superluminous supernova. We expect to be able to observe these with Roman out to a redshift of 6 or 7. And so that's kind of motivating the need for understanding near UV and far UV. Okay, so what are the challenges that we've faced so far? I think reporting and rapid classification. So this is both what Saurabh was talking about with sharing information in our community, as well as having telescopes throughout the world that can make these observations, so that if something is discovered in Hawaii, maybe somewhere in China can classify it or something like that. And that really shortening the time period between discovery and classification would be really helpful. I will also say classification is its own challenge. And so having those early observations help with that. The response time for HST, I've mentioned this is a challenge, and I think will only get harder with budget cuts and as Space Telescope's resources decrease. And if there's any way that we can fill in some of those gaps as a community, I think it would be great to discuss that. Far UV spectra and imaging in particular are very rare, and this is because you have that bright object clearance that you have to get through. So that ultra disruptive TOO is not allowed to have far UV spectra or imaging, and the Flex Thursday observations also cannot include the far UV. So this is something that we have to push on with normal disruptive TOOs. The Swift red leak in the UV filter, I think, has just made it challenging to use this filter for UV observations. So here are type 1a supernova spectra convolved with the different filter transmission curves. This is the one I want you to look at up here, the UVW2, and you can see that there's this significant near UV contribution to what was intended to be a far UV filter. And so that contaminates this and makes it less useful than I would like. Swift is just a less sensitive instrument than HST, which is fine. I love the rapid turnaround time, but that means that it's only really giving us good spectra for very nearby bright supernovae. And then finally, because there aren't that many UV observations, there aren't that many UV models. And so a lot of modeling papers only focus on the optical. So I want to encourage all of the theorists out there to model the ultraviolet as well, discuss that in your papers. So the UV future is bright. We have small missions which are being proposed to try and observe in the UV. We have ULTRASAT. This is going to provide near UV imaging with a rapid response time of 15 minutes and a 5-minute cadence for a single field. We have UVEX, which is going to be giving us far UV and near UV spectra with a response time of less than 3 hours. So both of these are going to bring us to parameter spaces that we're not currently exploring. And then the Habitable Worlds Observatory, I think, is very promising, but only if we can have TOO observations. So I hope that's a discussion that we have here and something that we can lean on as this mission is developed to increase those capabilities. And then with the high redshift, with Roman and Rubin coming online and JWST already, this is a place where I think both our near universe can inform our high redshift universe, and our high redshift universe can inform our nearby universe. So to summarize, we're still in this phase where every supernova spectrum we get is unique. The iron group elements are providing line blanketing, which suppress the UV flux and make it essential to get early time observations. But these observations give us information on the ejecta properties like clumping, tell us information about shock breakout and shock cooling, which gives us progenitor information, information on the materials surrounding the stars before they explode and their mass loss histories, the progenitors of type 1a supernova, high redshift universe. And then finally, I think future missions are really going to increase our sample size and push us to earlier times so that we can learn even more about what's going on in these stars. Next.
Very nice talk. Maybe we have time for a question or two.
Yeah, it's clearly valuable to observe these supernovae as early as possible, but we have to go from photometric detection to spectroscopic classification to submitting the TO to getting the data. going forward, which one do you think is the biggest bottleneck, and where would you dedicate time or resources to improve our efficiency?
For me, the biggest challenge is, I think, I want to say classification. And this may be a problem that we write our proposals, in that we know it's a supernova, and often we need to know what type of supernova it is before we observe it. And often it takes 12 to 24 hours to get that classification spectrum. So I think with our wide field surveys, I think we're getting more rapid observations and higher cadence observations. So we're discovering things early. We still are often at a 24-hour discovery window, so pushing that would also be awesome. And I think we're working with telescopes to get like very rapid, swift turnaround time. But that discovery and classification can often take 2 days. And when you're waiting like every hour, those 2 days take an eternity.
Yeah, maybe one more question. Alex?
Yeah, Osley, in your plot of spectra showing the diversity of the type 2s, how close in phase were those different objects? Because, of course, the spectra changed so quickly that it might be a fair comparison.
So those are all around day 20. So I would say the biggest uncertainty is 99 EM, because it doesn't have a very well-constrained explosion epoch. But given how suppressed the UV flux is, think if anything this is kind of its maximum. All around day 20. So day 10 and day 20, I think, because of your programs, are the epochs that we have the most observations at, and by most I mean like 4. Yeah, those are all at the same epoch. I mean, another idea I have is maybe we shouldn't be talking about things at the same epoch. Maybe we should be talking about things at the same temperature or something like that.
Should I use?
What's that? I think doesn't matter. I think. Okay. Oops. Great. And so next, Chinan Wang will talk about very high cadence observations with Kepler TESS and future missions.
So, hi everyone. So I'm Chinan Wang, and I'm currently a TESS ULTRASAT Joint Fellow at MIT and Weizmann Institute. So today I'm going to share about how the transient science can benefit from the high cadence observations from space missions like Kepler and TESS. So I'll start with introduction with the instruments and about the science, also continue into the science cases, in which I will mainly focus on the early time of the supernovae and also some discussion on the exotic transients. But in general, so Kepler and TESS has observed many other interesting science cases which I cannot cover due to the time limits, like the binary evolution, the stellar flares, AGN and TDE. So apologize if I missed some of your favorite science case, but they are covered in some following talks, including Michael Fassner's talk in this afternoon, and Rand Dingler is also going to talk about some AGN science in his poster. So for people who are not familiar with these two telescopes, these are originally designed as the exoplanet hunters. And their survey strategy is to basically gaze at a large patch of sky continuously for a long time with extremely high cadence. So for Kepler and TESS prime mission, it's 30 minutes cadence, and in the extended mission 3, TESS team has successfully reduced that to the 200 seconds cadence. And here is the bandpass for your reference. You can see the Kepler is basically composed of BV, RI bands, and TESS is a combination of the RIZ bands. And this actually makes them also a very good machine to detect the fast evolving transient phenomena, as chances are that when the supernova or transients explode in their field of view, the TESS, and we can get high cadence light curve for these transients before the explosion to the later phase for free, basically. So transient scientists can take a free ride with these exoplanet hunters. So what are the science cases we are interested in? I'm going to start with thermonuclear. And So as introduced by Azali in previous talk, so we have long questions about the progenitor of type 1a. We know it's the explosion of the white dwarf, but the issue is what's the donor of in the system. So you can divide them into the double degenerate system in which the companion is a white dwarf, and the single degenerate case where the companion is is a main sequence star or a giant. And depending on how the explosion happens, you can further classify them into like the deflagration models, or whether the deflagration turn into a detonation, or maybe the explosion starts with a detonation and turn into another detonation in the center of the stars. So those are all the dimensions of these type 1a models, and many of them may correspond to subtypes of the type 1a, and it's our job to figure out what's the connection in between these models and observed type 1a's. So the hint for this, to distinguish these models, like in the early time. So Dan Kaysen first put forward in 2010 that when the supernova ejector collide into the non-degenerate companion, you form both shocks that creates a lot of radiation in the extremely, especially in the bluer bands, UV, and also some in the optical bands. Those early access of bombs will normally last for less than 5 days. And people figure out that later that besides interaction with the companion, you can also have a lot of other mechanisms creating similar early access. For example, in the double detonation case, in the double degenerate case, when the companion, a white dwarf, get tidally disrupted, it will form a dense CSM around it, and the collision of the ejector with the CSM will create another shock. Or if you somehow get like radioactive isotopes get mixed into the shallower layers of the ejector, it will also create some early access, or maybe the first detonation at the surface will create some other radioactive isotopes. So all this will create early access, and we need tons of observations, both in the light curve and in the color information to distinguish them. So that's why we would like to look into the Kepler and TESS light curve. The first example is 2000 Kepler supernovae 2018 OH. So on the upper right plot here, you can see the beautiful Kepler light curve, and after you can clearly see that the rise part seems to compose of like 2 rising components, and after subtracting a smooth power law rise, you see early access like features, which last for around 5 days. And combined with other observations and model fittings, we've kind of find some, we still have some difficulty in determining the exact progenitors. The light curve fit seems to prefer the double detonation model more, but other models also give pretty good fit within 0.1 magnitude difference. And the early color shows that it's kind of blue early access, which is consistent of companion interaction models. But late time spectral observation kind of rule out this possibility because we did not see the helium and hydrogen that get expelled from the companion star as expected in the single degenerate case. So in terms of other type 1a observed in Kepler prime and extended missions, it seems that all of them match smooth power law rise pretty well. So in combination, we have around 10 type 1a in Kepler missions. So far, only one of them shows the early access, the 18OH. So it's still a kind of small sample to say anything decisive about the progenitors. So that's why we need more samples from TESS. And throughout the past 7 years, TESS has observed more than 300 of type 1As. And the first one actually the first normal type 1A that we see has early access is 23BE. So it actually takes a long time. And so this plot, I compare that with other high cadence light curve of type 1As in Kepler and TESS samples. So the blue points are the 18OH and the black points are the 23BE. And in the residual plot, you can see the 23BE seem to exhibit early access with a similar morphology as that of 18OH, but with like half of the intensities. So this is further confirmed by the Swift observations that you see some early access feature as Ali also mentioned. But again, also as Ali has mentioned that we find that all of these models doesn't seem to fit the TESS light curve and multiband light curve and the UV light curve pretty well. Like the companion interaction model and the CSM interaction model seem to, while they can give a good fit to the TESS-like curve, they seem to give a too strong or sharp early access in the UV part, which is not seen. And for other two models, while they do give us more smooth early access in UV, they seem to have larger deviation at the later times. So it's very, so issue in these models may lie in that it's very hard to model the line blackening effect at the early time. So future improvements in the modeling will be very important for, yes, many of the future missions will probe into the UV, like ULTRASAT and UVEX. And so I want to further show another peculiar type 1a, shows a sharp, the 21ZNY showing a sharp early access here. So so the 2003 FG-like type 1a also sometimes also called the super Chandra type 1a because they are mostly over luminous, and in order to expand their luminosity, you need a super Chandra mass progenitor if the produced radioactive isotopes are all to explain the luminosities. So, what's special of this event is that you can see in the insert here. So the test, the early access in the test band only lasts for around a bit more than 1 day. So that's very different from what we see from the previous two examples in which the early access lasts for around 5 days. So these short features cannot be well explained by all the other models except for the CSN interaction model. So combined with the spectroscopic observations, we can kind of confidently conclude that the best explanation for this object is that the progenitor system consists of double white dwarf binaries, and then when it's spiraling, the companion get tidally disrupted by the primary white dwarf and form a dense CSM around the progenitor system, and the interaction with that creates early access which we see here. And as that also naturally explains the super Chandra nature of this object. So as I said, TESS has accumulated a pretty large sample of type 1a. So we can take a step back and see what's the rate of the early access and the demographics of the early access. So it's kind of interesting that we only have seen two normal type 1a with early access, the 18OH and 23VE, as I said later. So I want to highlight a study led by Michael Fassner, in which he analyzed pick out the 74 high quality type 1a in TESS before 2023, and claims that there is basically no non-detection if you compare that with companion interaction model. So I would say so there is only like 3 tentative detections in the sense that it only match same as detection in the Bayes factor criteria, but get rejected in the variation information criteria. So that's actually gives you a pretty extremely low rate of the early access, and that's kind of interesting because in some other ground-based survey we do see a larger rate of the early access. Like for ZTF sample, we see 3 in 30 type 1a with low redshift sample, and after efficiency correction, you can they claim that the rate is like 10 to 30%. And another KMT net sample is 5 in 19, but they are observing that in the bluer bands, in B and V bands, in which you do expect the access to be stronger. But there seems to be some tension between these results, but I also want to say that those results are all carried out in different bands, and they have different definition of the early access features. So in order to reach some consistency within the results between different surveys, we kind of need to understand this a bit better, trying to reach an like agreements about what's the proper definition of the early access and the prediction from different models. So that's for the type 1a. And next, I'm going to look into the core collapse supernovae. As Ali explained, one interesting features at the early time is the shock breakout and cooling effect. So what happens at the early time of core collapse is that so sorry, I put a video here, but it could not be shown somehow And anyway, so what happens at the first few minutes or hours is that the shock of supernova explosion will propagate within the stars, and when it propagates onto the surface of the star, it will the shock will break out from the surface of the star and creates a very bright flash, which is extremely bright in UV and X-ray mainly. And that lasts for around a few minutes to a few hours. And following that, the photosphere start to expand, and the shock-heated envelope of the progenitor star will start to cool down, and that brings a second phase called the shock cooling phase. And then you start to see the main peak powered by the radioactive decays. And luckily, we do see likely see both progress in the Kepler and TESS missions. So left-hand side, I show you a tentative detection of the shock breakout of the Kepler supernovae 2011D, and you can see spike here, which is likely from the shock breakout, lasts for around like 3 to 4 hours. And this the model fitting indicates that it's really inconsistent with a progenitor star of like around 500 solar radius. And on the right-hand side, I show you two supernova with shock cooling peak detected, the 17 JGH by the Kepler mission and the 21 ZBY by the TESS missions. And I want to, from the model fitting to these two models, we find that their progenitors are consistent with red supergiant or yellow supergiant with radius ranging from 50 to 300 solar radius. And that results actually is inconsistent and comparable to the other studies of other type 2Bs at much shorter, much lower redshift, in which you are able to get some direct pre-explosion image from HST. So we kind of show that with the high cadence light curve, you can give good constraint onto that and extend those redshift limit to a higher range. And so in this slide, I want to highlight the importance of the high cadence light curve of those Kepler and TESS. So this is basically the fitting of the 2017 JGH waves, and without the Kepler data, and the color lines are basically the posteriors of the best speed models. And you can see without the early high cadence data, the best speeding models just like you get extremely wide scatters, and which doesn't seem to match the non-detections of the Kepler pretty well. So I guess one conclusion we can draw is that the early observations will be very important, especially you want to nail down the time of explosions and the rise speed. So next, I'm going to talk about some exotic transients, including gamma ray bursts and fast evolving ones. So there has been a lot of like exciting recent progress in the detecting the gamma ray burst afterglows with TESS missions. So by like actually a few different groups. So I want to highlight a few interesting results recently. So for example, in the study led by Rahul Jayaraman, he finds that there seems to be some fine structure in the TESS light curve in which you see these Gaussian-like bumps after like around an hour after the gamma ray burst triggers, and these bumps can likely be explained by the reverse shock in the gamma ray burst. And this is a study led by a group in UCanterbury, and in which we find that there seems to be some time delay between the alert of the trigger of the gamma ray burst itself and the onset of the afterglows, and that delay is on average 900 seconds among like around 7 afterglow we detected. And I also want to highlight orphan gamma ray afterglow 2019 PIM study led by Dan Purley, and in which you see a relatively slowly evolving gamma ray burst afterglows that can be probably well explained by the dirty fireball models. And in Kepler and TESS, there is also a lot of like fast evolving transients that you are not able to wasn't able to discover from the ground-based surveys. So left-hand side shows a good example of that. So that's why in the Kepler mission, and we kind of want to continue that effort in detecting more anomaly or exotic transients in TESS field of view. That's why we start this program called TESSalite, in which we do blind search for the transients in the TESS field of view. And in total, we get like around 45,000 objects. And that's most of them are actually stellar flares or the moving objects like comets and other galactic objects. So what we do, it will take a lot of effort to like filtering that. So what we do is we start a citizen science program on the Zooniverse, in which we have like over 1,000 of volunteers in helping with classifying and categorizing those transients detections. And as I just checked this morning, that we luckily reached the 100% completion now. So next step, we are going to like look into the exact interesting transient and going to announce the detections soon. And also later in this afternoon, Michael Fassner will also talk about his studies on the blind search of the transients in TESS. So please feel free to drop by. And last but not least, I want to talk about the future missions. I think many people have already talked about the ULTRASAT, and I'm extremely excited about that because it's also a wide field high cadence survey, and in particular, it's looking to the UV range in which a lot of the aforementioned early fast features like early access, shock breakout, and coolings are predicted to be predominant. And Avishai is going to give a talk on these Thursdays. But I also want to mention the next generation planet hunters that have the similar design as the Kepler and TESS, including the Plato mission led by ESA and the ET2 mission led by China. And actually, I want to make a call to the transient community that I think it's the time that we can actually put some input into these two missions, as now they have already realized that we can actually do a lot of cool transient science with these exoplanet hunters. But the issue is that they don't know what's the right thing to do, and there's a lot of issues. For example, how to set up a alert system, alert streams, and there's also some like realistic problems that they want our advice. For example, their data downlink is strongly limited by the bandpass, and the result is that you are not able to download every high cadence 4-frame image onto the ground. So we have to choose whether we want a low cadence 4-frame image instead, or do we want to look into the high cadence region, but with more restricted fields. So I believe that's some questions that our transient community can give a lot of like suggestions on. Okay, I think it's right about the time, so I put my summary slides here and happy to respond to any questions. Okay.
So in terms of that last question you brought up in terms of downlink, is there, do you think, any possibility of having like a transient detector on board that would then download postage stamps if, like, I don't know, you could do quick difference imaging or something like that?
Yeah, I hope so. I think that's something I discussed with the PI of ET2, and he's really interested in that. The issue is that for the spacecraft, before launch, we don't know what systematics we'll get. So it's really hard to write a pre-designed algorithm and put them in the satellite before launch. So like in TESS, we spent a few years in figuring out what are the systematics and how we can efficiently reduce them. So I think maybe it will be doable, but it will take a few years in general. Yeah.
More questions?
Thank you for the wonderful talk. I'm curious for figuring out what's the mechanism for the early access. Other than the photometry, is there any other signature we're looking for trying to differentiating different models?
Yes, the color information is one important thing because different models like the K10, the companion interaction model gives you a much bluer much bluer early access, and then as Azali shows earlier, you have like a very sharp early access in the UV. And another thing is, of course, the spectra, but the main issue is about the modeling because you have a lot of lamp blackening in that so far, I've seen a few spectral comparison with the models, and none of them are very statistical. So I would say it's still a very hard thing to explore.
Any last questions? Okay, well. All right, Dan Purley is next here. Let's see, let's find your. Oops, okay. Fumbling. There you go. Okay. So there you go. So he is going to talk about ultraviolet spectroscopy of voluminous fast blue optical transients.
Okay, thanks. Thanks for the opportunity from the organizers to speak here as well. So I'm going to speak about what the slide title says, spectroscopy of a luminous fast blue optical transient. What is a luminous fast blue optical transient? So we're going to have to dig a little bit into the history here, since I know not all of you work on this particular obscure type of transient, but I would like to convince you that this is a very interesting obscure type of transient. So the history of this goes back to the surveys in the 2010s that were expanding our view of what the time domain sky could produce in the optical beyond the classic supernova classes, type 2, type 1c, type 1a, superluminous supernovae. These low luminosity transients were being found by these surveys. And also a population was emerging, reported by people like Maria Drought and Panstars, of transients with characteristic timescales in the day regime. And these were given various names that essentially just told you what they were, such as fast blue optical transients, or rapidly evolving transients, or fast luminous transients. And it wasn't known what they were because they didn't have any well-established analogs from the literature, and they evolved too fast and were too rare to have dedicated follow-up. And so for most of the previous decade, it was a population of events that was known from these surveys, but it was not exactly well understood what they were, but largely suspected to have something to do with, say, circumstellar interaction around an otherwise normal-ish type of supernova. Now, these kinds of optical surveys have improved over the years, and in particular, the Zwicky Transient Facility, with its reliable 2 to 3 night cadence, was very effective at uncovering large samples of things in this particular parameter space of a few days to a week, and luminosities comparable to that of supernovae. And so a few years ago, Anna Ho and collaborators, including me, were able to take the population of things that were previously in this box and bin them into classes. And there's at least 3 very different types of things in this box, some of which are, depending on your perspective, more interesting or less interesting than others. So for example, we have the 2Bs, which are generally double-peaked explosions, but they have an initial peak that's very fast, very blue, and reasonably luminous as well. This is a well-understood thing, and usually they have a second peak, but occasionally the second peak is much weaker than the first peak, and they just look like a fast blue transient. Okay, so that's a relatively well-understood process. I would not call that a new type of transient. There is a rarer and more luminous subpopulation of supernovae called 1BNs and now also 1CNs. So these are genuinely fast transients, timescale of about a week to rise and to decay. They are definitely associated with strong circumstellar interaction around probably a massive star explosion, and they have very strong emission lines that makes them very distinct. But there's also a third population, which is different from these other 2, which is what I'm going to be focusing on in this talk. And this is sometimes called the cow-likes. I'll get back to that in a second. Sometimes called LF-BOTs, luminous fast blue optical transients. And these are very distinctive because their spectra are entirely featureless, or almost entirely featureless at all phases. They have very luminous radio emission, very luminous and highly variable X-ray emission, and they never have any spectrum at any phase that is analogous to any type of supernova that we know. So they are a genuine mystery. And one of the reasons that we know as much as we do about the subpopulation is thanks to this event, AT 2018 COW, or the COW, as we like to call it. And it is really what drove our knowledge that these are very different from other types of transients and probably have a very different origin. So just to list its primary unique properties, the rise is extremely fast. It's not a week, it's not 4 days, it's 2 days in the optical to go to a luminosity higher than that of any standard core collapse supernova, about -20 in the blue bands. Its spectrum temperature remains hot all the way to late times. 20,000 Kelvin, it's still 20,000 Kelvin even after it's fading, which means the photosphere is actually shrinking, not expanding at basically every phase we could observe it. It never shows any broad features. The only features it shows are very weak and they're intermediate in width, a couple thousand kilometers per second, and they're hydrogen and helium, and they have very strange line profiles. They also only emerge relatively late. As I already mentioned, luminous X-rays, they swing up and down by an order of magnitude on timescales of about a day, implicating some sort of central engine. Very luminous self-absorbed radio millimeter emission, suggesting some sort of very fast energetic shock in dense material. And then more recently, it's also emerged that it's left behind some sort of very hot tens of thousands Kelvin remnant of about an AU in size, but still thousands of solar luminosities after a year. Okay, but it's not the only event now. So since that time, we've been hunting for others in CTF, and so have other people. And they're starting to become a population. And the general messages of this populations are similarities yet differences. So the Bilk properties that I described for AT 2018 COW, the COW, hold up for these other events as well. The rise times are reasonably similar, plus or minus a few days. The temperatures are similar. The temperature evolution is similar. Some of them remain slightly brighter at late times, but they still fade quite a bit from the peak and never show anything like a supernova. There have been a couple of surprises. So aside from the late time emission from the COW itself, some other events have shown some interesting behavior. One of them is that CSS 161010. It also showed hydrogen lines. It's one of the few other events that actually has late time spectroscopy to show these intermediate width lines. They're actually blue shifted all the way offset from the central of the H alpha line, so suggesting some component which is completely displaced in velocity from that of the progenitor and the host. And then another crazy thing that we discovered a couple of years ago was one of these events actually started producing optical flares that went up and down on timescales of just a couple of minutes and then went away. And then there'd be another flare which would vary up and down erratically for a few minutes and then stop again. And again, implicating some sort of central engine, some sort of emission process that we still don't really understand. So there are a lot of mysteries of these things. We would really like to know what they are. It is telling us something genuinely new out there in the cosmos, which might be coupled to other things that we're interested in. So some of the things that we think we know and are pointing us in the right direction is the rise is very fast, luminosity is very high. That means it's very energetic. The variability is fast, both at early times and at late times, and it produces high energy emission. So that it probably involves some sort of compact engine, like a black hole, or maybe a neutron star. The optical radiation fades very fast, never develops broad lines, no radioactive tail. That suggests there's very little ejecta, very little radioactive ejecta, so it's not something like a normal supernova. The radio millimeter emission suggests very high densities and a very energetic shock propagating into those high densities, but then it cuts off after about 6 months and declines very fast, which suggests there's some sort of bubble of pre-existing material that was there before the explosion got going, that was put there somehow. And then we also now know that there's interesting things going on at late times from this hot UV source and also now these optical flares, which suggest that there is still energy input from a central source that lasts for not just hours, days, but actually for months, maybe years. So there's different categories of models. It could be some sort of very unusual type of massive star core collapse, maybe a failed supernova, given the lack of ejecta and this sort of late time source, central engine. So that's one category of models. Another category of models attribute it to accretion of an object onto a TDE, maybe in a binary or maybe an intermediate mass black hole in some sort of cluster. Either way, this is very interesting. This is telling us something about exotic fates of massive stars that produce transients that are very different from what we know about. The other might tell us where intermediate mass black holes are. So even though this is a very obscure type of transient, and there's only, count on one hand the number of well-observed examples that we have, is telling us something very interesting about objects out there in the universe. Okay, so we have lots of data on all these things. Until lately, until in fact a few months ago, one thing that we have been lacking is a high quality ultraviolet spectra. So these are, to remind you, ultraviolet transients. They peak in the ultraviolet and they remain in the ultraviolet at all times. So what we would really like to do is to capture an ultraviolet spectrum, because the optical spectra are featureless. They don't tell us very much. We would like to see what's going on in the ultraviolet, where there's lots of line transitions, and potentially we could learn a lot more. So for many cycles, we've had a program to hopefully get a UV spectrum of a fast optical transient. And finally, in the latest cycle, we had a transient that satisfied the criteria to trigger on it. So it's this one, AT2224WPP. For those of you who don't know, I like to name all these things after animals. And so probably this is going to be the whippet, since it kind of matches the TNS name. But anyway, regardless of what it is, observationally, it is a very nearby. It's one of the nearest LF bots, cow-like objects that we have to date at redshift 0.09. It was found early by ZTF. It's very luminous. It's actually significantly more luminous than the cow itself. And most importantly, it was actually visible to HST despite the one gyro stuff. You know, when the gyro thing happened, I thought, oh man, this might be done. We're never going to get a good event. And then we had this, and it was fantastic. So we were able to get both COS and STS spectra all the way down to the EUV of this transient. And we excitedly downloaded the data, expecting to see all sorts of amazing line transitions and other new features. And here is the spectrum combined with an optical spectrum that's more or less simultaneous. And amazingly enough, it is basically just a black body. There are no intrinsic features that I can recognize, and I've scrutinized this for a while now, at all, except for absorption lines from the Milky Way and from its dim, faint host galaxy at redshift 0.08. So we've been able to match all these things with well-established ISM lines that you see in other classes of transients. Haven't seen any clear features that are attributable to the transient itself, which is pretty amazing. So to compare that, this is another type of fast, hot transient with evolves on similar timescales in similar ways. This is a 1CN that was also observed by my HST program a few years ago, and it's just totally different. Like there's no comparison between these two things. So the 1CN spectrum, just to zoom in here, you see all these deep P Cygni lines. You know, they go almost to zero flux, and they have emission that is many times the continuum. That's in ultra or in purple here, and 21 CSP, just flat continuum. So maybe, you know, you could attribute this little dip here to some sort of broad line perhaps, but it's not obvious. You know, we have Lyman alpha from the host galaxy. Okay, that's not a surprise. But no intrinsic features, quite amazing. So here for comparison are some other UV transients. So there's 2023 IXF. That is, you know, as you all know, that is a type 2 supernova with some circumstellar interaction at early times. You know, it's got features, not strong features, but it definitely has features. We would have seen those features if they were there. Here's a TDE, so possibly these things are TDEs. I think there's some evidence that this might indeed be evidence towards it's a TDE, but again, we don't see the same exact features that we see in other TDEs that have been observed in the UV. So it's a bit of a mystery, but it's certainly telling us something. So to sort of sum up here, what we have is a hot blue spectrum with no intrinsic lines, no emission lines, no absorption lines, no neural lines, no broad lines, basically all the way down to the Lyman limit and a little bit past Lyman alpha. So what does that mean? Okay, you have to go back to your rate of transfer and scratch your head and think a little bit. And, you know, this is still a work in progress for figuring out everything this implies. There's a few ways to get a very hot UV source with no lines. It can have a sort of very dynamically thin surface. So that there's not enough, you know, optically thin space to generate the lines. That doesn't seem too likely for most of the progenitor scenarios. There could be no UV absorbing species in it at all because it's perhaps too hot. That doesn't really fit the thermal nature of the transient and the SED very well, since the temperature is not that high. An extremely high velocity, which is appealing, except for the fact that later on we have optical spectra, which, like AT2018 COW, do show weak narrow features at velocities of a few thousand kilometers per second, so not high enough that you would smear out the strong carbon-4 and other features that you might expect to see from some sort of stellar wind, because we know there was material around this thing prior to the explosion from the radio, from the fast appearance of the UV. So it's a bit of a mystery, but it is certainly telling us something. So yes, now in terms of what do I think this is telling us? So I think for many years we've been going back and forth between, is this some sort of stellar thing or is this some sort of tidal disruption? And I think this swings pretty strongly in favor of more tidal disruption models, because for any stellar model, you really do need lots and lots of mass being ejected right before the explosion somehow. And that mass is coming off in a high velocity wind. There's going to be lots of it all over the place, and it's going to be hard to not produce some sort of line signatures that we would see in the HST spectrum, unless the transient had already swept all of it up. But then it would be cooling down, and it's not cooling down at these phases. It's still very hot. Whereas in the TDE model, maybe you have more flexibility with inhomogeneities and streams and other things, perhaps. It's just like a sort of less well understood process. So maybe there's more ways to get out of this. For example, these asymmetries. So if you have ideas, please talk to me, because I would like to know. Yeah, so then to wrap up, I know this is a very hard thing to do. It's been challenging, but we're hopeful that new surveys are going to find more of these things and eventually turn single objects into samples.
I think an important clue to this is this TSM. And
we wrote a paper saying maybe there was a dust echo from the cow. Maybe there's other interpretations. Is there anything further on the infrared and whether that could be telling us about the environment for any of the non-cows?
The infrared is hard because the infrared is faint, and these things are generally not as close as the cow. So it's not been easy to get late time infrared. So we did try for this latest event to get some infrared, and I was unsuccessful. So I hope other people were more successful at getting some late time infrared to add to the light curve. I don't see any evidence for an infrared excess in this object, but we don't really have the right observations at the right phases to be certain. Yeah, that is another clue.
Oh. You don't see any magnesium 2 even in the ISM. It's like the line ratio between the lack of Mg2 and
I believe there is magnesium 2 in the ISM for this object. Yeah, so the signal noise is so there's a close cost estimate in STS spectrum. The signal noise is lower in STS in part because it's fainter at those wavelengths. Yeah, I mean, so it's in a very low mass, low luminosity galaxy, and it's in the outskirts. I don't have a galaxy image here of this object. So the ISM transitions are pretty weak in it. I'm sure there would have been magnesium 2 in there clearly, and maybe there is. I'm not seeing it here either myself. But I think that's explainable. But we certainly don't see a strong line of it from the transient. Like we also don't see carbon 4 or any of those other classical strong transitions from the transient.
All right, great. All right, great. And then our last speaker for this session, Erez Zimmerman, will talk about ultraviolet observations of infant supernova.
Hi, everyone. I'm Erez Zimmerman from the Weizmann Institute, PhD student. And so today I want to talk about infant supernovae. So infant supernovae, as discussed earlier, are supernovae discovered soon. We define it as 2 days after null detection. And because they are typically very, very hot at discovery in the early phases, they are also UV bright, which is compelling to observe with UV instruments, which of course is done from space. So what can we get from UV information on these infant supernovae? First of all, we can get the shock breakout pulse, which we discussed, which is UV and X-ray bright, but this requires an instrument that would detect the supernova at discovery. Then we can probe the CSM interaction. So a lot of these supernovae have circumstellar material around them. This can be done with UV spectroscopy, photometry, and also it can be done with X-ray. And lastly, we can follow the supernova as it starts to expand and cool down. So this is the shock cooling emission, which can be done with UV photometry. But all this information is lost very early, either because the phase is moving to a next phase or the UV is becoming dimmer and harder to observe. So let's go one by one with these types of observations and see what we can do. The first thing is the shock breakout. So we have the core collapse creating a shock wave through the star. As the shock wave goes to the surface of the star, you start seeing the first photons come out of the exploding star. So the breakout flash is UV and X-ray bright, and this was actually detected serendipitously in the past. So we have at least one example of such X-ray burst from a supernova shock breakout, and would reveal a lot of the progenitor properties if they could be systematically detected, which hopefully they would be with ULTRASAT and also wide field X-ray surveys that are coming up or already observing. But what happens to the shock breakout when you have circumstellar material? So you start with the star, there is an explosion, the shock moves through the star, but now when it reaches the surface of the star, it meets a optically thick circumstellar material, and the photons can't just escape. So what you're starting to get at this point is that the photons only trickle slowly, and then you have an extended shock breakout phase, which affects, well, basically everything. It extends the phase, also creates a peak luminosity that is typically brighter, and creates early spectroscopy that shows narrow line emission, typically from ionization of the CSM. And the UV observations, the early UV observations, are really critical to probe the CSM properties and density, because, well, you need a full SED to really see what the luminosity is and probe what the mass is, etc. So we have one really good example of a supernova that happened really nearby, that is 2023 IXF, and we can follow what can be done with UV to probe such CSM. So first of all, we can see the extended shock breakout when we look at the bolometric luminosity of the supernova, and this can only be done if we have UV observations. Otherwise, we would be underestimating the luminosity. But also, we would also miss the temperature. We wouldn't see the peak temperature because we will be in the Rayleigh-Jeans tail of the black body distribution. So we won't know what the peak temperature of the supernova is. So we can not see basically the supernova heating and the extended shock breakout, and we won't really be able to tell if there, well, what is the measure of the CSM shock breakout really. And with these bolometric properties, we can actually probe the mass in the confined shell of the CSM. We can actually say by the luminosity how much mass we have in this confined CSM, which can probe the mass loss as well if you take into account the extent and the shock velocity of the supernova. Okay, so the shock moves through a confined CSM. We probe the amount of mass that we have in the CSM, but then the shock reaches a new phase of the CSM, and we start seeing X-rays. And the reason I call this a new phase of the CSM is because the X-rays are 2 to 3 orders of magnitude less bright than the UV optical, which means that you must have had a drop in density, which we named the extended wind. So you have the confined CSM, which creates the extended shock breakout, then it moves into the extended wind later down the line. But the mass loss of this extended wind is still quite high, at around 10 to the minus 4 solar mass per year in the case of 2023 IXF, which means that you still have too much mass loss to be regularly explained with typical red supergiant wind values. So we don't necessarily see this in non-exploding red supergiants. Okay, so moving on to ultraviolet spectroscopy and what we can do with it when looking at interacting supernovae with CSM. I'm talking about type 2 supernovae. So we have only 2 examples of these short interacting supernovae, and I think this is actually probably a type 2N, so probably only one regular type 2 supernova that has this confined CSM, and that is 2023 IXF, and we have the spectra here. So we can actually see that while we have the narrow lines from the CSM, the flash features, we can still see the narrow lines in the UV, and we actually have lines developing as we get more spectra in later phases and developing while we have photospheric features. And with the narrow lines, we can use all sorts of techniques to probe the chemistry and also the density of the CSM. For example, the width of the electron scattering wings of the narrow lines tells us where the optical thickness is at roughly at 1. The chemistry is basically seen from the elements that we see from the different spectra. Now, what's interesting about having UV spectra at all? I mean, we see it from the optical. Why do we need to extend it further to the blue? Well, the lines in the UV persist longer, it seems, and probe the later ionization source of the supernova. So there must be more interaction happening. So here it's already at day 9, whereas in the optical you barely see any lines already. You can also look at the narrow ISM line. So you see the line of sight chemistry when you look in the UV, and you can basically tell something about the metallicity of the supernova. There's also a lot of like photospheric science that you can do. So for example, the photospheric features in the UV start developing before the optical features, and this happens typically at around 15 kilokelvin. So that's also quite interesting to look at. And what we're missing, and I think this is a recurring theme, is the far UV. Extending this even further would be very interesting for interacting supernovae. So you have, for example, a very strong helium line just at the edge of what we can do with the near UV. So this could be done with, this could be combined with like optical helium lines to make abundance studies. And you can also probe the chemistry better if you have more lines. And for example, if you have Lehman alpha, you can actually say what the metallicity of the ISM line of sight is, which we can't without going further to the far UV. So overall, if you take everything, the spectroscopy, the photometry, and the X-ray, you can actually sort of create a map of the CSM around an exploding star, like 2023 ISF. So you have the dense CSM, which you see from early UV optical. Then you have the drop in density that you see because the X-ray is not as bright, which you can see with the X-ray. And further down the line, you actually see radio. And I think someone is working on fixing the radio and the X-ray together to a unified model. But that is just one example. And it's always more interesting to look at populations and many supernovae. And we actually have in the literature examples of more such interacting heating supernovae. So these are, for example, the heating supernovae. So there's several examples where we see that the UV color is becoming bluer early in the supernova interaction. And this is a sign of heating. So these are heating supernovae in opposed to cooling supernovae like 2013 FS. So these are interesting, and we're already starting to see a population. Next, we can look at the X-rays. So the X-rays are more abundant than we typically think. So this study by Irani is showing that a lot of supernovae actually have X-rays coming from late time emission. So that would be the extended wind. So this drop in density is probably pretty common. So you have the confined shell, and then you have an extended wind coming out, and this creates several possible breakout scenarios, actually. So one would be the classical one from the stellar edge, one would be in the dense CSM, and the other would be at the edge of the CSM if the CSM is so thick that the shock will only break out at the edge of the CSM, and these could be further investigated. Lastly, we can talk about shock cooling. So an extensive study about shock cooling was done by Irani et al. As well, in which we found out that only half of supernovae fit the shock cooling model. So only half of type 2 regular supernovae seem to be able to produce progenitor properties with shock cooling models. The other ones miss the rise in the UV, are too UV bright compared to what you expect from the shock cooling models. And there was also one example of these hitting this hitting supernova. And outside this sample, you actually have things like 2024 GGI, which is another 7 megaparsec supernova, which if we would have detected further away, we probably would have missed the rise as well, and we would classify it as a 2C- in this classification scheme, which would say that we would miss the rise and say it doesn't really fit shock cooling. But it doesn't stop us from trying to look at what the shock cooling model would look for, something like a 2024 GGI. So the early light curve for such a supernova, a 2C minus supernova, if you will, shows that the early light curve is really dominated by the interaction, and you can actually fix the 2023 IXF bolometric light curve and in time and luminosity, and sort of see that they act similarly. But then you do sort of can see the t to the minus half decline that you expect from shock cooling models. And this is because probably a lot of the early photons coming from the star are trickling out now, and you actually see the expanding star, which is the shock cooling phase. But unfortunately, there is a big question about what it means about the progenitor properties, since there's also a validity domain to these models, which can only be implemented until hydrogen recombination. After that, it becomes the ejector becomes transparent, and you can't really say a lot about the progenitor properties properly. Okay, so to conclude my talk, UV observations are critical for early core collapse supernovae studies. Shock breakout pulse will reveal progenitor properties with future UV and X-ray surveys. CSM interaction is cool, and we need UV to study it, and X-rays. Yeah, shock cooling also probes the explosion physics, CSM abundance, and progenitor properties. All of these need the UV and X-ray observations. So thank you very much.
For the 24th ZZI, in the earlier light curve, like at least in our study, we found that it had like two different slopes. Like, do you see that in your data?
Well, not in the data that we have from Electro, but I mean, I do see it in your data. Yeah, but the two slopes are actually, we also observed it in 2023 IXF. So, and this is also an upcoming work. Yeah, one thing that this means is that when you take into account the explosion time, you have to think about how this slope changes in the early observations when you really try to set the explosion.
Sort of a random question, but when you see the X-rays, and what is the UV at that time doing? I mean, is the idea that it's the forward shock and the X-rays are heating, half of the X-rays are coming to the observer and half of them are heating the ejector?
Yes, so the idea, what we did in 2023 IXF, we basically said that as the shock travels to behind CSM, it is actually relatively dense. So it is being efficiently cooled by inverse Compton scattering, which suppresses the X-ray. So we showed a calculation that shows that this could be the case. But then when the shock goes into the extended wind after the drop in density, you no longer have efficient inverse Compton cooling. And then you start to see X-rays because the electrons are much lighter.
You still have heating of the ejector also at that phase?
I think the X-ray basically starts on day 4, and this is a big bin from Swift, and the heating basically stops here. So it does seem like it's transitioning into the extended wind when the X-rays start to be observable, at least from Swift. Of course, it would be better to use like larger X-ray telescopes.
I think we're out of time. Everyone's getting hungry, but I encourage keep the conversation going at lunch and on Slack. Let's give the round of speakers. We have a lot of other wavelengths to cover, but let's enjoy lunch. For lunch, quick announcement. There's going to be a tight seating. We have a big crowd, and we also have the rest of the Space Telescope staff down there. So in addition to the cafe, there's also the conference room in the back that can fit about 30 or 40 more people, Cafe Con. I believe that's open. Also outside, I think it's nice enough. There's a bunch of benches and tables, and you can also bring food throughout the lobby. Is Mia here real quick? I don't know. There's a sign-up sheet for community science with Roman on the front table. If anyone wants to sign up, she posted a sheet there. We'll do 1 hour. We'll make back a little bit of time. So we'll meet back here at 1:45. That should be enough, and we'll see you all soon. Thank you.